The master file table is a relational database that is central to the New Technology File System, or NTFS. NTFS has been the primary file system in use by Windows since around the year 2000. Windows 95 and 98 used a file system called FAT32. FAT stands for File Allocation Table. The 32 represented the size of the clusters which served as entries in the table. Each entry in the file allocation table was 32 bits. That is, 4 bytes or 4 double character representations in hexadecimal. Each of these 4-byte hexadecimal entries pointed to an address in memory that contained either file contents or metadata. The successor of FAT32, NTFS, became the primary file system with the release of Windows 2000 and is still used with Windows 10. The new Resilient File System, or REFS, is supposed to eventually replace NTFS. But until that time comes, NTFS is still the primary Windows file system that is used. The master file table stores records which provide metadata for every file on a computer. Each and every single file and folder on an NTFS computer has a corresponding master file table record, including one for the master file table itself and its copy. NTFS has 27 system-reserved files which it uses for journaling, security, and optimization. Why is the master file table important for forensic examiners? Even if a particular file or folder has been deleted and wiped from permanent storage, with the file's master file table record, you can prove that the file existed, right down to its exact size, creation date and time, and the addresses in memory where the file was stored. With a master file table record, you can manually locate and recover all of a file's component clusters and reassemble them. This video is part 1 of a structural breakdown of the master file table record. I will start with the general layout of the record. Next, I will move to the record file header, which begins every record in the table. In the next video in this series, I will break down the structure of the blocks known as attributes that reside within the master file table record. Let's begin. A master file table record consists of 1024 bytes of data. The first 512 bytes is where the majority of the forensically useful information resides. The second 512 bytes only contains data if the size of a record's corresponding file is less than 512 bytes. When this is the case, the file is called resident, and the file's contents are displayed here. If the record's corresponding file is greater than 512 bytes, then the file is called non-resident. The clusters which make up the file are stored throughout permanent storage. The addresses of these clusters are displayed within the data attribute located in the first half of the record. If you look at the very last 2 bytes of the master file table record, you will notice the 2 hex values F7 and 04. If you look at the last 2 bytes of the first sector, you will see the same 2 bytes. These bytes are the update sequence number for this particular record. The update sequence number is an error checking code which is defined in the first half of the master file table record. The purpose of this code is to ensure that there were no problems encountered while the record was saved to memory. The end of the metadata portion of the master file table record is identified by a series of 4 double Fs near the end of the first sector. The overall composition of the record will depend on what kind of object the associated item is. If the record is for a folder, the data blocks contained within will be somewhat different than those for a file. The master file table record for a folder will contain information blocks for detailing parent-child relationships that exist between the containing structure and its subcomponents. This information would not be necessary for a text file or an executable, so those information blocks will not exist in the record. A master file table record like the one you currently see on your screen is for a text file. Records for files such as this will have the same general structural composition, which consists of a series of blocks called attributes. These attributes contain all of the forensically useful information about an object, such as a Word document, an MP3, or a video file. The structure that is generally seen is the following. First, you'll have a header, which accompanies every master file table record, no matter what type it is. Next, a standard information attribute block, which always begins with the hexadecimal signature 10000000. Next, a file name attribute block, which begins with the signature 30000000. And then finally, a data block attribute, which begins with the signature of 80000000. In the following section, I'll break down the subcomponents of the file record header. In part 2 of this video series, I'll break down the standard information, file name, and data attribute blocks. I will now go over the file record header. There are very few tutorials available which cover this subject. The ones that are available tend to take a generic approach where samples are taken from a master file table record and decoded. I have not seen a demonstration yet which covers in detail the differences in Windows versions. If you view a sample taken from a Windows 8 machine like the one you see on your screen, it will not be decoded exactly the same as a record taken from a Windows 7, Vista, or XP machine. The primary structure of the MFT record remains the same throughout all of these versions. However, there are enough subtle changes in the coding for the file system that a new reference chart is required to fully give the subject justice. It is the job of the examiner to be familiar with these changes, so he or she can know how to interpret them as an expert. This demonstration will provide a complete breakdown of a Windows 8 master file table record. This knowledge can be taken as a reference when approaching older or newer versions of Windows. The master file table starts with a 4-byte opening signature which spells out file in all capitals in ASCII. In hexadecimal, this signature is 46, 49, 4C, 45. The next field represents the offset to the update sequence, which is part of the error checking mechanism for the master file table. The offset, read as little endian, is 0030, or 48 in decimal. This means that the update sequence value is 48 bytes from the first byte of the master file table. The next field, 0003, or 3 in decimal, represents the size in words of the update sequence array. A word is 2 bytes counted together. The value of this field means that the entire update sequence array is 6 bytes in size. The next field, which consists of 8 bytes, is the log file sequence number. This value, read as little endian, is 05, F1, 5C, D3, 70 in hex. When this value is converted to decimal, it is 25,524,228,976. This is the entry number for one of the system-reserved journaling files maintained by NTFS. The next field refers to the sequence number. This value increases every time the record has been accessed and then released. In this case, the hex value of 0B50 means that this record has been accessed 2,896 times. The next field is the hard link count. The number in this field refers to the number of directories which reference this particular file. This prevents the need for duplication. Read in little endian, this value is 0002 in hex, or 2 in decimal. So 2 directories are referencing this one file. The next field displays the offset to the first attribute of the master file table record. Hex 0038 converted into decimal is 56. So 56 bytes from the first byte of the record will mark the start of the standard information attribute, which begins at offset 56 of the record with its signature of 10000000. Bytes 22 and 23 of the file record header display the record status flag. This field says whether an object is a file or a folder and whether it is currently active or deleted in an unallocated space. In byte 22, a 01 represents a file that is in use. A 00 is a deleted file. A 03 is a folder that is in use. A 02 is a deleted folder. This particular record is for a file that is currently in use. Bytes 24 through 27 represent the actual size of the master file table record. In other words, this is how much data really makes up the 1024 bytes of allocated space for the record. This record shows a value of hex 01E0, which is 480 in decimal. This is the size in bytes of the amount of data within the record. Bytes 28 through 31 refer to the allocated size of the master file table record. This is the total amount of possible available space for data. You saw this number also defined within the volume boot record. The value for this field is 0400 in hex, which is 1024 in decimal. Bytes 32 through 39 refer to the base master file table record. When this field has all zeros for a value, it means that it is the base or highest level parent record. When the value in this field is not 0, it is a pointer referencing the file or folder's parent master file table record. If there is more information about a file than there is space in the allocated 1024 byte record, the additional information will be stored in subsequent master file table records. All of these related records will point to their respective parent records in this base file record field. The 8 bytes in this particular record are all zeros, so this record is a base file record. Bytes 40 and 41 are the next attribute ID. If you count all of the attribute blocks in this master file table record, there are 4 of them: a standard information attribute, 2 file name attributes, and a data attribute. The decimal 5 value at bytes 40 and 41 means that the next attribute to be added to this record would bring the total count to 5. Bytes 44 through 47 refer to the master file table identification number. The identification number for this particular record is hex 31, or decimal 49. Bytes 48 through 53 combine to form the Fixup array. Bytes 48 and 49 are the update sequence number. This is the value that was originally referenced at bytes 4 and 5 at the start of the file record header. For this particular record, the update sequence number is F704. Bytes 50 and 51 refer to the values that were originally stored in the last 2 bytes of the first sector. If you look at bytes 511 and 512 of the first sector of the master file table, you will see that the update sequence number, which is listed at bytes 48 and 49, are stored there as well. The update sequence number that is stored at bytes 48 and 49 must match the values that are stored at bytes 511 and 512, otherwise there will be an error. The update sequence number must also match the values that are stored at bytes 511 and 512 of the second sector of the master file table record. The bytes stored at offset 52 and 53 of the file record header are the values that were originally stored at offset 511 and 512 of the second sector. This process is what Microsoft uses for error correction. Knowledge of this process may seem trivial and unnecessary. However, it does come in handy forensically when determining whether there are problems processing or updating certain files during an examination. A good example of this was something that I saw recently. I deleted a file from a thumb drive that was reformatted as NTFS. The file was no longer on the media as far as the file system was concerned. However, when examining the deleted file's master file table record, it said that the file was still in use. I imaged this thumb drive using FTK Imager and examined the forensic image using autopsy. During the initial examination, the deleted file did not show up in the high-level navigation tree along with all of the other recovered files. I had to navigate to Autopsy's unallocated space search tool to find the deleted file. Sometimes, just because a file or a folder does not show up in the recovery bin of a forensic tool does not mean that there is nothing else there to be found. Having the forensic knowledge of how files are stored, retrieved, and recovered gives you the skills to more effectively identify and recover such misplaced files. In the next video in this series, I will do a breakdown of the standard information, file name, and data attribute blocks.